Carl, allow me to very briefly introduce you. I know that people can see you, can see your bio in the schedule there. Carl Solder is the Chief Technology Officer for Cisco Australia and New Zealand, bringing over 35 years of experience in ICT leadership, engineering and innovation. He previously served as Vice President of Engineering at Cisco's global headquarters in Silicon Valley, where he led enterprise networking and cloud initiatives. I think over the break someone was talking about wanting to hear more about cloud. Carl began his career in Perth and has held roles across Asia Pacific, specialising in network architecture, cybersecurity and digital transformation. He is a very well-respected voice in the tech community broadly, well beyond the remit of Cisco as a company, across technology very broadly. I've heard him speak before. He's very interesting to listen to. He's the champion of simplicity in IT design. Carl, the floor is yours.
Thank you very much. All right, I'm going to take you on a journey today, a journey into the wonderful world of quantum. So, back in the 1950s and 60s, it was all about the mainframe. We saw the rise of the mainframe and the emergence of computing into the enterprise space. In the 1980s, actually, when I was doing my university degree, my undergraduate, we saw the rise of the PC, the personal computer. Anyone remember that? But back in probably the late 1990s and the early 2000s, we saw the rise of mobile computing, especially in 2007, when Steve Jobs got on stage and introduced the iPhone. And in the 2010s, it was all about cloud computing. We've seen the rise of cloud computing and use of that cloud computing resource to help accelerate enterprise businesses. But we're now on the precipice of another revolution, the revolution into the world of quantum. Now, back in 2019, Google actually worked on a project they called the Sycamore project, a Sycamore processor. It was a 53-qubit quantum computer that they claimed could process a workload in 200 seconds that would take a traditional supercomputer some 10,000 years to process, to kind of give you an idea of the order and magnitude of scale. So when you start to look into that, you start to ask the question, like, what is behind this? How did Google achieve this? And it comes down to some principles in quantum mechanics, and specifically this notion of the qubit. The qubit, like the bit that we use in traditional computing, is a store of information. But unlike a bit, a qubit can actually hold two values at the same time. So a bit is either a 0 or a 1. A qubit can be a 0 and a 1 at the same time. And this leverages the power in quantum mechanics, a thing called quantum superposition. And this fundamentally drives the ability and capability of how we can take quantum computing and make it exponentially faster than traditional computing platforms. So I want to kind of spend a little bit of time understanding the power of the qubit. It's important to understand this to then, in order to understand what quantum computing is all about. And I want to use an analogy, a little bit of a story here. So if we go back centuries to this folklore of this Chinese farmer who invented the game of chess. So enamored by it, he got an audience with the Chinese emperor at the same time, showed the emperor this wonderful game of chess. The emperor was so impressed, he said, "I will give you any reward that you want." And so the farmer, being smart, said, okay. He put a grain of rice on the first square of the chessboard, and he asked the emperor, can you double the amount of rice for every square that's on that chessboard? By the 10th square, the emperor owed him 512 grains of rice. By the 20th square, the emperor owed him over 500,000 grains of rice. By the 40th square, it was 1 trillion. And by the 64th square, it was 18.4 quadrillion squares of rice. More rice than actually existed in the entire Chinese empire at the same time. So what you're seeing here is the power of doubling. The power of doubling. And that's effectively what you have with quantum. Because with each additional qubit, you effectively double the processing capability of that quantum computer. So you go back to that Google Sycamore processor, 53 qubits. You might think a computer with 53 bits is not going to amount to much. But in the quantum world, 53 qubits is an awful lot of processing and compute capability. So much so that when you look at the Google Sycamore processor, one of the things that qubits can do and quantum computers can do is they can process things in parallel at the same time. And so in effect, it's a big number. I'm not going to kind of rattle that out. But that 53 qubit quantum computer could hold and process that number of values at the same time. Now that actually equates to about 144 petabytes of memory in today's world. 144 petabytes, it's a lot of storage. Now you go from 53 to 54 qubits, and all of a sudden now you can process 288 petabytes of data. You go to 55 qubits, you can actually process 576 petabytes of data. So you start to gain an appreciation of the power of what quantum computing and that qubit enables that quantum computer to do. All right, so that's the opportunity. So where's the industry right now at with qubit scale? So back in December 2023, IBM created this Condor ASIC. It actually has 1,121 qubits on it. So think that 53 qubits back in 2019, 2023, we got to 1121. More recently, Caltech actually announced that they'd built a system with 6,100 qubits. Again, you start to think of the doubling capability from 53 to 1121 to 6,100. You start to think, okay, that's a lot of processing capability that we're building into these systems. But there is a challenge with all of this. The challenge is that qubits are highly unstable by nature. And in order to effectively use a quantum computer and use those qubits, you basically have to get a collection of physical qubits and create what's called a logically error-corrected qubit. And that logically error-corrected qubit is the point at which you can then start to really utilize the power of quantum computing. So how many physical qubits does it take to build a logically error-corrected qubit? Well, the industry is continuing to improve that process. You know, a few years ago, Google had the number down 49 to 1. More recently, about probably 2024, I think it was, Microsoft and Quantum actually got it down to 30 to 4, which is effectively 7.5 to 1. So they're continually trying to find ways in which they can reduce the number of physical to logical. Okay. All right. So the industry overall is in effect focusing on quantum stability as opposed to building out an at-scale device. And if you think about it in the traditional sense, that's what we did many, many years ago. The whole move from mainframes to PCs was to leverage the power and effectiveness of distributed computing. And that, in effect, is what we're also heading towards doing in the quantum computing space as well. Rather than building this big behemoth of a quantum computer that has, you know, thousands, tens of thousands, hundreds of thousands of qubits, why not we leverage the power of distributed quantum computing, bring it together, and overlay some software on top so that we can make that collection of multiple physical quantum computers look like one. So the promise of quantum, what can we do with this? There's a lot of opportunity that quantum now presents. There's many industry verticals in play right now who are looking to leverage the power of quantum computing to solve use cases that are specific to their business. And there's a lot of industry verticals that are probably leading the charge. Pharmaceuticals, banking are probably a big one, aerospace, energy, defence, healthcare. All of them are looking to leverage quantum computing. And I kind of want to spend a little bit of time talking about some examples. So DHL, a courier delivery service. They're looking, for example, at a use case in New York City, taking telemetry from sensors across the traffic systems, figuring out and optimizing routes for delivery drivers. Delivery driver has to get a package from point A to point B. Traffic is all over the place in New York. How can I optimize and get that package to my destination as quickly as possible? Taking a telemetry and actually real-time providing changes to routes for the drivers. This is going to reduce wear and tear on the delivery trucks. It's going to improve customer satisfaction because you're getting packaged to them quicker. You're also reducing energy consumption in potentially sitting, waiting, idle in traffic. You're also looking at companies like Airbus, looking to use quantum computing to streamline and optimize the aerodynamics of the planes that they're building. Looking at using quantum sensing to actually take in telemetry to optimize the flight patterns. Using quantum cryptography to actually secure transmission from pilots to air traffic control and backwards and forwards. You start looking at Woodside Petroleum. I was at a mining roundtable earlier this year. I was quite surprised that the CTO of Woodside stood up and said, yeah, we've been using quantum computing for quite some years. I was like, well, okay, did not know that. One of the areas they're looking to use that is to optimize manufacturing catalysts to refine the manufacturing of liquid natural gas. Quite interesting. This is a really interesting one, Goldman Sachs. Many banks are looking to utilize quantum to get an edge in the market. If you start thinking about how you can use that processing capability, if you're looking to make a trade, making statistical predictions on where the market might go, being able to process thousands, millions, tens of millions of calculations on statistically which is the next best bet to place. That's an interesting leverage. So you start thinking about it. Already, high-frequency trading could definitely leverage this. There's another interesting one that I'll talk about a little bit later on, where the New York Stock Exchange, NASDAQ, and those kind of companies are also looking to make it fairer and more equitable for different banks to leverage their systems. Because the challenge you have right now is if I have the rack where the trading actually happens in NYSE, there's a lot of jockeying for position to get your rack as close to that rack as possible. Why? Because the speed of light. If I am a rack here and then someone over here is a rack here and we have traders who hit the button at the same time, guess what? That rack that's closer is actually going to get to the trading system servers just that nanosecond faster. So they have an edge. So how can we actually make it fairer for all banks and bypass that issue of transmission and the speed of light? So I'll talk about that in a moment. This is another one. Obviously, drug research companies looking at doing simulations to try to figure out ways in which we can actually cure some incurable diseases today. So drug manufacturers are also looking quite heavily to leverage quantum to drive drug research. Now, there's obviously a lot of good that we see that can happen with quantum. You saw some great examples there. But as Frank said, a hammer can be used to build a house. It can also be used to kill someone. For every good that a tool can be used, there's also a bad side. And the same is with quantum. There are risks with quantum. And the biggest risk that we have today in the industry is this worry that someone might use a quantum computer to crack today's encrypted data. Considering 95, 96% of the data that crosses the internet today is encrypted, it's secure, or so we think it's secure. What would it take to actually decrypt that? You start thinking about nation states leveraging the power of quantum computing to compromise and actually snoop in on our encrypted data. It's a concern. The industry's coined a term Y2Q, years to quantum. This is not Y2K, Y2Q, years to quantum, the time it's going to take before a quantum computer is commercially viable and available to start decrypting data real time. And the industry estimates that we're probably 5 to 7 years away from that potentially happening. So it's a real concern. Governments, banks, intelligence agencies are all concerned about this right now. I'm talking to banks here in Australia who are looking and worried about this right now, as an example. So the question then becomes, back to our good friend the qubit, how many qubits does it take to break today's encryption? Well, the answer is 4,000 qubits for the RSA encryption. There's two main encryption technologies, RSA and AES, that are in play today for most organisations. Around 6,600 qubits for AES, around 4,000 qubits for RSA. Now that, by the way, is logically error-corrected qubits, not physical qubits. So if you take the analogy of maybe 10 to 1, then we're kind of looking at around 40 to 60, 70,000 qubits. So keeping in mind, we're currently at around about 6,100 qubits. You can probably start to appreciate that as we continue to get better and better and better, and also as we start to network different quantum computers together, then it's not going to be too far away before we get to something where we could be cracking today's encrypted data. So that's a worry. All right. So even though we don't have that number of qubits today, we still have another problem. So the industry's coined this term HNDL, harvest now, decrypt later, or store now, decrypt later. And that is the issue where someone actually initiates a man in the middle and connects and snoops and copies the data that's encrypted, and then stores that data away for a rainy day until the quantum computer becomes powerful enough to then decrypt it. So even now you can imagine a nation state in a submarine going to a transatlantic cable, tapping in and actually capturing data that could be going between intelligence agencies, for example, and then storing that and maybe a couple of years down the line decrypting it. It's a worry. So the industry is already starting to think about what can we do today to actually change and innovate to build quantum-resistant encryption technologies we can start implement in our solutions today to protect. Now, the threat you kind of think is a few years out, but you're also starting to hear news like this one here, Chinese researchers who claim they've actually cracked it already. Whether this is real or not, no one's been able to ascertain, but you have these claims and it does raise concern and alarms in a lot of organisations. So this is a problem. This is a threat. This is something that we all have to figure out how that we circumvent. All right, so that kind of gives you a lay of the land as far as what's happening out there in the industry, a little bit of an understanding of what's behind this quantum computing paradigm. But I do now want to kind of shift gears and talk a little bit about what Cisco's doing in the quantum space. Cisco actually last year, or was it this year, I can't remember, early this year or late last year, we actually opened up our quantum research lab in Santa Monica. That's right now kind of centre of where most of the quantum research is taking place. So we're partnering with a few universities and research laboratories in and around the Los Angeles area. And Cisco is actively working on a number of solutions that we're looking to bring to market. And actually have already started to introduce some prototypes already. So what are we looking to do? We're looking to build a full networking stack to support the interconnection of distributed quantum computing nodes, effectively to build a quantum network. A quantum network is very different from a traditional network, and you'll get to understand why that is in a little while. But I want to kind of use an explanation here, and I'm going to use the IBM Quantum System 2. This is a picture of it. It's a quantum computing platform that IBM is marketing today. Now, the way this thing works, if I kind of go through some of the basics, there is a chip in there called the Heron chip, and the quantum computing system that IBM set up is made up of multiple interconnected Heron chips. Each of these chips is, I think, 156 qubits. So what happens is that they start to build this thing out. It's modular. You can see that kind of star topology of that top-down view of the quantum computer. Each one of those arms has a collection of these Heron chips. And so as you need to scale out and add more qubits, you add another arm. Right? So it's almost like a modular Lego kind of approach that they're using to build out that capability. But even within that confines of that particular setup, you get to a point where you max out the number of qubits you can put inside of a physical machine. And so what happens then is you start to then have multiples of these to interconnect together. And that's where Cisco comes into play. When you get to the point where you have multiples of these X's, you can see here, these quantum computing nodes, we have to start finding ways in which we can connect and interconnect them. So that's what Cisco is about, is building that networking stack, that little octagonal blue thing that you see there. We're looking to build, that is a combination of network interface cards, it's the network devices, it's the operating systems, it's the quantum protocols in order to facilitate the movement of quantum data between those nodes. Very, very important. All right, so I'm going to make all of you experts in quantum networking right now. So I'm going to give you a little bit of an explanation on how a quantum network switch actually works. It's quite fascinating. And it leverages, again, quantum mechanics capabilities, what Einstein called spooky science. And it's this thing here, quantum entanglement. So we talked about quantum superposition, which is the ability for a qubit to hold two values at the same time. This is the other one, which is also quite interesting. Quantum entanglement is the process where you take two qubits and you entangle them, and then they share a state such that if the value in one of those qubits changes, instantaneously the other qubit also inherits that same change, that same state. So if I have a qubit A over here and a qubit B over here, I change the value in qubit A, instantaneously qubit B inherits that value. Now, the interesting thing is that physicists don't know how this works, but they can demonstrate it working. They don't know how it works, but they can demonstrate it working. That's why Einstein called it spooky science. All right, so understanding that you have and want to transmit some data. We have two quantum computers, one on the left, one on the right, and in the mix of all those qubits, there's a qubit on the left with some data in it. We want to get it to the qubit on the right. So what will happen is, and this is how it's a little bit different, because in today's world, we basically convert that bit and we send it as a photon or an electron down a copper wire or a fibre cable to get it to the other end. We can't do that in this particular case. So what actually happens is that we have to use a thing called a quantum entanglement source, which is going to be the switch or the quantum network device itself. And what happens is we actually create a set of entangled photons. A photon is a qubit. A qubit is anything which is a subatomic particle. You can think electrons, you think photons is an example. So what happens is that these photons, you call it A prime and B prime. They share the same state. We'll then send those photons over terrestrial wire to each of those quantum computers. And then what happens is on the left-hand side, qubit A will entangle itself with that A prime. And when it does that, right, in effect what happens is that you then create a multi-entangled collection of qubits, and that value will then get transmitted magically without going over a wire to the qubit B prime on the other side. And then what we would do is we would effectively then bring that fourth qubit, which is in the bottom right here, and bring it into that entanglement process to collect that data, and then the exchange has happened. So there is a combination of using terrestrial connections to actually get those photons to the other end, but we actually use this notion of entanglement. Now, entanglement, theoretically, you could have entangled qubits light years apart, and theoretically they should be able to maintain consistency and state, theoretically. There are some challenges right now. I'll kind of talk about that in a moment in terms of how far they can support this in today's world. But that's the kind of thing that we're looking at. Now, Cisco, earlier this year, actually launched our first quantum chip. It's an entanglement source. It actually generates 200 million entangled photon pairs per second. So when you start thinking about you want to exchange data, you obviously want to be able to exchange a lot. So this is our first instance of technology as part of our quantum networking stack, this quantum computing chip. All right. So there are some challenges, of course, that we also have with this as well. And that is that research still needs to focus on improving and expanding our understanding and capabilities of what this technology can actually do. So ideally, we continue to like to see to build out a larger quantum computing stack. As I said, 6,100 qubits is the current record that we've got right now. Quantum coherence, actually maintaining that state, is also very, very important. The current record is about 5,500 seconds. We'd like to maintain and keep it more. You might see that with quantum computing, they typically operate in very controlled environments. Typically, a quantum computer, in most instances, needs to operate at almost 0 degrees Kelvin. So that's a very specialized environment. One of the things that we're doing on the quantum networking side, and why we're using photons, is that in a traditional quantum computing space, environmentals can actually have an impact on the stability of that qubit. So by using photons, they're impervious to heat, temperature, humidity, that kind of thing. So we're hoping that we can actually build quantum network devices that can operate at room temperature. Entanglement distances, 750 miles right now. Operating temperatures, we want to get to room temperature if we can. Improve transmission fidelity. We also want to develop a whole lot of protocols that support and facilitate that quantum network. And last one there that we see there is achieve longer quantum memory. So we actually have to store this stuff too. So building quantum memory is also a part of the equation that we have to complete when we're building out our quantum networking stack. So how do you get started? If you are interested in quantum, there's actually a couple of resources and a couple of opportunities you do have to take advantage of. Obviously, engaging with quantum research and quantum communities is one thing. Did you know that there are actually quantum computing cloud resources that you can leverage today? Amazon have got it, Microsoft have got it, Google have got it, IBM's got it. So if you want, you can actually go and subscribe to those services today. They actually have those services on offer. Also, Cisco themselves have started to make available some quantum networking design kits. So this is a quantum network design simulator that you can actually build out your quantum network and actually run real traffic across it, confirm that your design is actually working. So that's something that's available from Cisco if you are interested. But anyway, I kind of wanted to finish off by saying that this interesting space of quantum computing, I believe, is going to have a dramatic impact on society overall. It's going to let us compute and understand things that maybe we've not been able to do with the current technology that we have in place today. So a lot of organisations are looking to leverage the power of quantum to drive new outcomes, to solve maybe unsolvable problems that were there in the past. But it's also going to represent a great opportunity for techies like us to get our hands onto some of this cool stuff and broaden our understanding horizons beyond where we have been today. But know that Cisco is committed to focusing on building out that quantum networking stack. We estimate that we're probably 12 to 18 months away from getting our first quantum network device prototype. And from there, probably another couple of years before we can actually start making that a viable solution to sell in market. So hopefully that gave you a good understanding of what's happening in the wonderful world of quantum, and maybe answer some questions later on that you might have based on what I've talked about today. Thank you very much.